There's a lot of variety in approaches in the field right now, both in terms of the types of signals. So many people are going for what's called closed loop neurostimulation, where they're identifying biomarkers in the brain that are indicative of particular memory states and stimulating based on those control signals. So that's one type of difference amongst approaches in the field, and the other is in targets of stimulation. Where are you stimulating to improve memory? Our team, we were funded by DARPA in 2014 to the tune of about $24 million to undertake a pretty massive study of neurosurgical patients and brain stimulation and memory. And we didn't know where the ideal location or target for stimulating to improve memory was going to be. Hippocampus seemed like it would be a good bet, given all the wealth of literature that connects hippocampus to human memory. And we did stimulate hippocampus, and there were some modest results there, some not so great. But then by chance, we happened upon lateral temporal cortex, and we found a very reliable effect. We found that we were able to improve recall performance between 15 to 20%. And in some patients, up to 40%. That is, patients were recalling, on average, 20% more words on a given list.
Is anyone else kind of surprised that it works? Well, do we have a mental model for what happens mechanistically when you stimulate that cortical area?
Maybe you happen to stimulate in an intersection of roads, which is most effective, such as this. In case of Parkinsonian stimulation, the subthalamic nucleus that has multiple projections from multiple motor areas.
I think that's right. I mean, we don't think that lateral temporal cortex is the spot for verbal memory in the brain. And in fact, what we see is that by stimulating, again, at this spot in the brain, lateral temporal, and at the right time, which is during these poor predicted memory states, you can change the larger brain dynamic. So you actually see a global or somewhat global change in the state of the brain network from a poor memory state, as defined by our multivariate classifiers, into a good memory state. And we published this in Nature Communications in 2018. So there's a localized stimulation that translates into more of a global state change in the brain through functional connectivity. And we think the effect is partly reliant upon connection with hippocampus. And we have additional data suggesting that the degree to which we're near white matter in lateral temporal cortex, and that white matter is connected to hippocampus, predicts the effectiveness of our therapy.
To add on to that, and thinking about the memory network as a network, indeed. I mean, on the subject of phase amplitude coupling, if you think about the hippocampus as a coordinator of like long range activity and synchronization between these memory areas, it's impossible to say I'm going to affect memory or improve memory in a clinical way without really looking at that whole network. And if you can find a hot spot like lateral temporal cortex that affects that whole network, then great. But I think this is going to be basically disease dependent. And from this, we can take a lesson from pharmaceuticals, right? We can look and say, okay, if I want to make a clinically relevant memory prosthetic or memory implant, I need to first look at what's going wrong, right? I need to understand how the brain's functioning when it's going right, and I need to look at how that deviates or when it's going wrong. And if I can restore that state, then I can probably restore function. And that's what we see, right? When we take these, there's a whole bunch of evidence, whether it's invasive intracranial stuff that came from Penn, or whether it's even non-invasive stuff done by Hanselmeyer or others. What you see is that networked coordination of activity and restoring that network activity at those multiple sites is what is critical to restoring function. I think there's a lot of evidence there, really strong evidence in humans to support that.